And begin.
Okay. Hello, everybody. My name is Gordon Rosner. I'm the president of the East Valley Astronomy Club. So welcome to January's virtual general meeting. As usual, I got the agenda up there, and you probably have been looking at that. We have two great presentations. Again, two great ones today. Tom Polakis will be doing a member presentation, and we have Dr. Travis Rector with us from University of Alaska at Anchorage. And he'll be talking about the composite images by professional observatories. So a lot of us are familiar because this is stuff that we're doing in our backyard. And so, the professional observatories are doing the same sort of thing. So we'll learn exactly what they're doing from Travis. So, as usual, welcome. Live long and prosper to everyone, especially in these troubled times. 2021 is here. Yeah, the big thing is 2020 is over. So 2021, it's looking promising. The board of directors and leadership team, we're starting to chat a little bit about what's going to be happening this year, later on this year, with hopes of us getting back together with some personal meetings and events going on. We don't know exactly when that's going to happen, but we certainly are hoping that it's going to happen sometime this year, probably later on. So, the usual introductions. This is the leadership team of the East Valley Astronomy Club. Give you a moment to just take a look at the names here. You have the president, vice president, treasurer, and secretary. And the board of directors are those club members who keep an eye out on the astronomy industry and just astronomy activities, because we go to them for votes on way that we are going to run the club. And then our administrators, Claude runs our observatory, the Gilbert Rotary Centennial Observatory we have. I'm in charge of the outreach. Property is David Hatch. Website, Marty does a fantastic job on our website and our newsletter, puts them together. And then observing is Wayne Thomas. Remember, we have a great observing program. So all those telescopes that everyone got for Christmas and are trying to figure them out in the backyard, we have observing programs that you can go and eventually get a plaque. And then our Astronomical League rep is Brooke Schofield, who's also our secretary. But down there, the most important member of the club is you. If we don't have you, then all these guys have nothing to do, and we want to keep them busy. So how do we do that? Well, dues are due for 2021. So it's especially important now to help the club and renew our dues and get us in a good position as we start opening up sometime. We don't know exactly when, but we're anticipating that we're going to start opening up and getting back to somewhat kind of normal. So please renew your memberships or join. Of course, you don't have to be a member to experience all of our Zoom meetings and everything that we do, but it helps the club if you're a member, and then you get a badge too. So club news, or rather the club olds. Again, it's a broken record. We still do not have any personal contact events going on. Meetings and outreach events. Our observatory is still closed. Still don't know exactly when, but we certainly have good hopes for sometime during this year. Member presentations. You'll see one today by Tom. Of course, Tom is a very prominent astrophotographer, so his level is pretty high on up there. But we want to have other people too. We don't have to have these fantastic photos that some of our basic, almost professional people have. We also want to see the beginners and what they're doing and their equipment and the problems that they have and things that they overcome. Or you just want to make a presentation about something, 10 minutes about that, and join on in. And it's kind of fun. You'll get to be able to make a presentation on a Zoom meeting. If you have any reservations about that, we can get together before the meeting, sometime that day or even a couple of days before, and practice and run through and just make sure that you're comfortable with it. And how do you get to be able to have a Zoom member presentation? Is let me know. And you do that via our website. So go on our website, that's EVAC Online, and at the bottom, there's links to the officers. Just press on the president link and an email format pops up, and you can just write whatever you want in there. And remember that the monthly meetings are being recorded, and the link is on our EVAC website. So if anyone missed it, go into our website, go into monthly meetings, and we will have a link. Just like we do, we have links on previous meetings also. So the Kalamazoo Astronomical Society in Michigan, Tom Mazden and Tom Polakis and myself, we were in a meeting with some other clubs around the country, just kind of exchanging some information on how we're doing during these troubled times. So we got to know the Kalamazoo Astronomical Society, and they're a big club, a very big club. And they're putting on an introduction to amateur astronomy course. It runs 5 weeks. It's not every week, it's every other week. But it starts at 1 p.m. Eastern time, which is 11 a.m. here, Arizona time. And it's free. All you have to do is sign up. How do you do that? Go down there and at their website, kasonline.org, just like ours is evaconline.org. Go to kasonline.org. And down at the bottom, there's a sign up, basically a sign up sheet. And then they will get the link to you. And so I'm pretty charged up about this because it's Introduction to Amateur Astronomy. And those who have been in the club, who were in it last year and the beginning of this year, we were going to start a program. We were just about to start it called Proto Stars, where we were going to have classes about beginning astronomy, beginning astrophotography, things like that. Generally, probably right before our general meetings. It would be in-person type of things. But as we all know, everything kind of came to a halt. So the Kalamazoo Club is putting it all online. So take a look. And we're still going to keep the ProtoStar program going, and you'll get a leg up on some of this. So it's free, it's open. I got a personal letter from the club, from the president, and said, let your club know, let everybody know that they are welcome to join in. Our next EVAC meeting is Friday, the 19th of February, usual time. And our main presentation will be about the Lowell Observatory and their present research capabilities and future views. So again, another great presentation with a local observatory here. So we'll jump into the member presentation. Tom Polakis, those who are in the club and those who search our Facebook page and know Tom, and he is a very accomplished astrophotographer and has been previous officers of the club and has really supported the club through all of these years. So we're fortunate he's going to give us a presentation on Jupiter and the Saturn conjunction, which I'm sure everybody saw. Right? Okay.
All right, ready to go?
John?
Okay, hi everybody. Happy New Year. I'm going to talk a bit about, first I'm going to share the screen. I guess it has to stop yours. Okay.
Yeah.
Everybody seeing that okay? Is that working, Gordon?
Yes.
Okay.
Looks-
All right.
looks good.
So yeah, let's talk about this for a while. This was something I didn't have real high hopes for early in the year. And then it ended up being one of my favorite astronomical events in over 40 years in the hobby. That was great. So I guess I can't see the titles of mine. I gotta make that thing go away. Come on. No, I can't see the top, but I know what it says. So what makes this event interesting is that it was very rare for them to get this close. So you always have Jupiter passing Saturn in its orbit, and the orbital period of Jupiter is 12 years, but Saturn's a moving target. It's moving in the same direction. So it takes about 20 years for Jupiter to catch up to Saturn and pass it. So you get that, but they're not going to pass real close to each other each time because the inclination, which is this angle down at the bottom to the Earth's plane of orbit, is not 0 degrees. So 1.5 and 2.5 degrees. So it's going to take quite the coincidence for them to be favorably placed along our line of sight. So one's not going to pass way above or below the other. So typically these closest approaches are about 1 degree, and this one was exceptional in that it was 1/10 of a degree, about 6 arc minutes. So we knew it was going to be both in a real high power telescopic field of view, and a lot of things were working against it. So we didn't know what exactly to expect. This is what happened in 1980. I was about 3 years into the hobby at the time. There was a triple conjunction, and that's Jupiter at the bottom, kind of doing retrograde motion to the west right now, and then it'll swing back again, and you'll have a third conjunction. So I list the dates of the 3 conjunctions there in 1980 and 81. And this was really cool because all 3 of those conjunctions happened while the 2 planets were pretty well separated from the sun. So you got to see this one in the morning sky, and then the next 2 in the evening sky. And I thought this is going to be fun to watch these, but I had no idea what was going to happen 40 years later. So what happened 40 years later is on this slide, and just ignore the pink dot as Pluto. I couldn't get rid of it in the simulation. So Pluto was next to these 2 planets the whole time, not that you would see it. And here comes Jupiter swinging back into direct motion in December, and you can see it at this scale, it just merges with it. It's important that the sun moves into the field of view. I'll talk about that later. So what you're seeing there is retrograde motion where they're both moving to the west. And then since Jupiter's on the inside track, it'll pass Saturn. These were done with Sky Safari, real nice phone app that I talk about daily with anybody who will listen. Next slide shows how I saw this conjunction was not as something that happened on December 21st. I saw it as something that developed for months and months because I was out imaging the planets in my driveway at every opportunity. I bought a color webcam, color planetary cam for the first time. And those things are amazing now. So, and I snapped off some pretty decent images of Mars and Jupiter and Saturn. Mars came to opposition, of course, this past year. And so I watched every time that I imaged the 2 planets, I watched them, Jupiter approaching, getting closer and closer, and then it split up for a little bit, and then watched the whole thing develop kind of in slow motion for months and months. And that's the way you should view astronomical events is you watch these things play out over months or even years. So a lot of talk about the Christmas star, and even astronomy got into it and called it the Christmas star. So I got kind of interested in that, like what would happen if you actually had the 2 planets merge so that you couldn't resolve them? Would it make something that was way brighter than Venus? And I think I knew the answer to that. But first, if you're talking about the Christmas star, here's the 3 wise men, and I have to show a Far Side comic. So. Okay, so what happens if you have 2 bright objects, but they're not equally bright, and they merge into one, so that what's going to happen to the total brightness when you do that? And so what I'm showing up at the top here, object 1, of course, is Jupiter. Its magnitude's -2 during the conjunction. Object 2 is Saturn, and it's 2.5 magnitudes fainter. It's a lot fainter. If you just do the math and see what do those combine into, it's negative 2.1. It's a tenth of a magnitude brighter, and you'll never notice that. So that was if they had merged into one. The brightest that so then what I did was just ran some scenarios, these 5 different magnitudes going up to where you have some hypothetical object sets that it's exactly as bright as Jupiter. That's the most magnitude gain you can possibly have. And even that's only 3/4 of a magnitude. So if you had 2 magnitude -2 objects merged into one thing emitting brightness, it would only brighten it by 3/4 of a magnitude, which you'd have to really even look to see a difference there. So the Christmas star to me was definitely not 2 planets that came to a conjunction so close that they brightened up, because they just don't brighten up. Venus is always going to be brighter than any of these planets as it is. Okay, so let's get to the images. This is not an image of the conjunction. This is my simulation. There are actual real images I took of Jupiter and Saturn, and they're kind of showing the challenge. One of the challenges of this event was that if you exposed for Jupiter correctly, which is what I did here, and then you just go and pan over to Saturn, which at the time, this was a couple weeks before the conjunction, that's how faint Saturn is going to be. It's 2.5 stops fainter than Jupiter. That's what that magnitude difference that you saw is going to do. The surface brightness is real low. And so I thought this is really not going to work, because you definitely don't want to expose for Saturn. Then you'll way overexpose Jupiter and you'll have blown highlights. There's nothing you can do when that happens to recover that photographically. So what I show on the right is what we want it to look like, where I imaged Jupiter, panned over to Saturn, and then brightened it by adjusting the gain by 2.5 stops. That's what we would have liked it to look like, and it isn't going to work that way. It's actually going to come out looking like that. So I was a little bit concerned that that's going to be bad, and then this is going to be bad. This is just a real simple simulation showing the sun and Jupiter and Saturn merged into one. Pluto, again, ignore it. But at the best, about when the sun is getting down to just past civil twilight, I guess it's 9 degrees or so here, Jupiter and Saturn are only going to be 15 degrees above the southwestern horizon as viewed from Arizona. And you typically don't image planets when they're below even 30 degrees. And they get down to 20, 15 degrees and they're just a mess, because you're looking through so much atmosphere and it's just boiling. So I was kind of concerned that that wasn't going to work out for us either, in addition to all the other usual concerns about it possibly being thick cirrus clouds or late monsoon clouds, whatever it would be. So I started out with this sequence, and this was kind of an aborted sequence. This is the worst of the photographs, but it was kind of just starting out because I have a 4-inch telescope mounted on my 12.5 out in the backyard observatory. And it was easy to open up and attach an SLR camera to it. And this is Jupiter and its moons as it approaches Saturn. So I just locked on Saturn for these 5 images. And then December 11th and 12th and 13th rolled around, and I had to do something that involved being away from the house, or it was cloudy, and I sort of gave up on the project. But this was kind of the trajectory that it was on. And even back on December 4th, you could put in an eyepiece and a little refractor that gives you 15x, a wide eyepiece, and you're already starting to get a feel for the event. So again, don't wait till the 21st and go out weeks ahead, months ahead, and watch this thing happening. It's so much more fulfilling that way. One thing that happened on the 4th, which was really cool, was that this is not the usual International Space Station, but it's the Hubble Space Telescope, happened to pass next to Jupiter and Saturn. So this is a combination of, I think it's 9 images, whatever the number in the dotted line. So just had the shutter on the SLR, so it was in sport mode. So it's just going to take a 2-second exposure, the next one, next 2-second exposure, and go across that way. And pretty cool. Passed right by Jupiter and Saturn in the evening sky in the southwest. Then it's getting closer still. This is on the 15th. I can't read the titles of my slides, so I think that's right. And So here's Jupiter and Saturn from out in the alley behind my house. There's absolutely no scenery and there's power lines everywhere and it's very urban. So I just put it over a neighbor's palm tree just to get all the settings right, because to me, one of the big events was going to be on the 16th when the crescent moon joined Jupiter and Saturn. It turned out that on the 16th, I was up in the Northwest Valley, up by 59th Avenue, actually by 75th Avenue in Bell. So it was a pretty short drive to go over to Thunderbird Park, which is some nice desert to frame the conjunction over the top of. And got this image of Jupiter and Saturn with the crescent moon, and then some saguaros, of course, in the foreground. So as this was happening, there were airplanes flying by all the time, which are kind of annoying, even though air traffic is way down. It's Phoenix and you have air traffic. And so I'd have to wait for the plane to depart the frame or before it entered the frame. And then finally, I just decided not to fight it anymore. And I'm just going to have planes going into the frame. And then this happened where the plane flew right in front of the moon. That made kind of a cool shot. These are typically 2 or 4 second exposures at ISO 800 with a Canon 6D and a 70 to 200 millimeter zoom lens. So now the big event was coming up, which was the 20th and the 21st. And I just thought I'd show the equipment here. So I used a 10-inch Dobsonian telescope. And what you see down here, it's a Dob, but you really need tracking to do this type of imaging. So down here is an equatorial platform. There's the motor. It gives you about 1 hour of tracking on that arc. It's an f5.6, so it's 1400 millimeters of focal length. The camera has a real cumbersome model number. QHY and ZWO, the 2 main Chinese camera manufacturers for planetary cameras, have this new color chip, a 462, and it's just terrific. It's amazing how sensitive it is, how light sensitive for a color chip it is. And I couldn't believe how good the results have been for all of that Jupiter and Saturn imaging that I was doing. You couldn't use a Barlow like you normally would with this type of imaging because you needed a wide enough field of view to capture them both because they're separated by over 6 arc minutes. I know it's super close, but that's still a lot compared to the size of both of the disks of the planets, which are only about a half an arc minute each. So the image scale, in case that means anything to anybody, is a lot larger than I'd usually use for planetary. Usually that'd be around 0.1 or a little less, and it's 0.4 in this case. But that's just so you can get that field of view to capture both of the planets on the chip at the same time. And so this is what I got on the day before, or on the night before closest approach. Here's the conjunction on the 20th, just prior to the conjunction. So there's a non-labeled. I was really pleased with this, and it's almost like, like Arizona or our longitude was the promised land, because we ended up with this thing happening the night before the conjunction with the great red spot right at the prime meridian, which is just terrific because you like having that in your Jupiter images. And then you had these 3 moons. There's Ganymede, Io, and Europa over there. So that was pretty cool. And then on the 21st, and what was surprising was that at this low 15, 20 degrees altitude, the seeing was, it's not going to be perfect, but the seeing was very much acceptable. And I learned from all this planetary imaging, at least from my local site, that the seeing is almost always the best for about an hour after sunset, hour and a half after sunset. Once we get that wind shift from the east with the drainage, then it's all over. Doesn't get as good for the rest of the night typically. So there's the 20th anyway with the labels on it, and here's the 21st. So that's closest approach. And, it was great that we had the great red spot right on the meridian on the 20th. And then what I knew it was coming on the 21st was that we were going to have a satellite. That was one of the 4 moons was going to be transiting Jupiter. And there it is. So you may think that's a shadow, but the shadow is actually not on the disk yet. Ganymede, against the brightness of being a little away from the equatorial band, is actually dark. It's seen in silhouette against the disk of Jupiter. So now we got those 2 moons and Ganymede in the shot. And You know, this is only shot at prime focus, or I guess it's called Newtonian focus of a 10-inch with only 1400 millimeters of focal length. So the image scale is not great. It's real low in the crud, in the atmospheric crud, but still start to see Cassini's division, and it's a respectable image of Saturn. And as for what I mentioned earlier, where Saturn was going to be grossly underexposed, I think this was another thing I was so pleasantly surprised about with this camera, was that I was able to just do a simple, in Photoshop, it's just called shadow highlight. And it's also a different way of doing curves. So that was a way to brighten Saturn. And I thought that would just be a big ball of noise, and it actually came out fairly clean. So all I did to do special processing to make Saturn appear like it was almost as bright as Jupiter was just to select it and brighten it up with curves that boost the shadows without affecting the highlights. And it came out okay. And so just for a second before I go on to this telescopic view at 150x is one of the highlights of all of my observing in astronomy. I've gone to the Southern Hemisphere 7 times. I've seen every bright deep sky object in every aperture up to 20-inch, north and south. And when anybody asks me what's the greatest thing I've ever seen in a telescope, it's the Shoemaker-Levy 9 impacts on Jupiter. Seeing those scars was just unbelievable in 1994, but this was close. It was just knowing what you're seeing, and the three-dimensionality of it was just remarkable. And I hope everybody got to see it at some point during those couple weeks around closest approach. We had plenty of clear nights in Arizona. We've had our clearest year since I lived here in 2020, and December was awesome. All sorts of clear nights. Well, almost done. Here's scaling back a little bit with the 4-inch refractor that I mentioned earlier in the backyard. These are 4 images that I took through a different planetary camera. This is a black and white done by QHY, another excellent camera. It's a monochrome camera. And in order to do this, I imaged during the day. So that's about 4 or 5 hours before sunset, like when the 2 planets are on the meridian, and that's an infrared filter, 780 nanometers. And I just wanted to put it into one sequence that would show the passage of Jupiter and then locking on Saturn in this case. So finally, surprisingly, astrology was very useful in this. So I went to my horoscope and per the Chicago Tribune, I looked up horoscopes from various sites, and every single one of them was different for a Leo on the night of December 21st, 2020. But it did say that as the tide ebbs and flows, remember to zoom out and take in the bigger picture. Look at all factors will bring you the clarity. So my takeaways from my horoscope was zoom out, then I knew not to use a Barlow lens. And bringing the clarity, that just meant use a 10-inch. Don't use the 15 or the 4-inch, and that would give me. So big thanks, big shout out to Chicago Tribune for their horoscope telling me exactly how to do the image. Hope everybody saw it. Thanks for listening.
All right, thank you, Tom. Gorgeous pictures as always. Gives us an incentive to get out there and start taking our own pictures. So Tom, Tamaz and I will hand it over to you to introduce Travis to us.
Okay, thanks, Gordon. Yeah, it's my pleasure to introduce Travis Rector. He's a professor of astrophysics at the University of Alaska at Anchorage. Some of his research interests are multi-wavelength observational techniques, young stellar objects in star-forming regions, imagery and visualization of research data, hard to say, but perhaps maybe more special than others, astronomy education research, which I think is really vital to see what the optimum ways are to get the younger people interested in the sciences and astronomy in particular. Yeah, today Travis is going to talk to us about imaging by professional astronomers and what that entails. And so normally I'd say please welcome Travis, but I'll say it anyway, and you'll hear some virtual hand claps. So go ahead, Travis.
Okay. Well, thanks everyone, and thanks to both the Toms for inviting me to be with you here today. So I'm going to go ahead and share my screen. Everyone see that okay? Thumbs up. Okay. So hi everyone, my name is Travis Rector, and as Tom mentioned, I'm a professor of astrophysics at the University of Alaska, Anchorage. And so what I'm going to do in my talk is just tell you a little bit about the work that I do in creating color composite images using data from professional observatories. So just a little bit about me. You probably don't know me by name, but I hope that you've seen some of my images. And so this image of the Eagle Nebula and then this image of the Helix Nebula are two of my more popular images that have been out there. And so just a little bit about myself. So I finished my doctorate at the University of Colorado back in '98. And after that, I came to here, to Kitt Peak, to start as a postdoc. And as I arrived at Kitt Peak, they were just commissioning a new wide field imaging camera that was called Mosaic. And here's a picture of the Mosaic camera, which consisted of 8 2K by 4K CCDs mosaicked or combined together to form a single 8K by 8K array. And so this was a 64 megapixel array, which even by today's standards is still pretty impressive. But back in 1998, it was a monster. And it was actually so big, storing the images that came from it was a real challenge. Each image that came off of this camera was 300 megabytes. And back at the time, the largest hard drive we had was a 20 gigabyte hard drive. And so processing the data was quite tedious and quite difficult. Now, this camera was interesting because it gave us a relatively wide field of view. It had a field of view of 1 square degree, which is roughly, if you hold your arm out at, if you hold your thumb out at arm's length, the size of your thumbnail will be about 1 square degree. So hardly wide field by camera considerations, but for a telescope, it was considered to be quite wide field. And so one of the first things I was asked to do, well, one of the things I was asked to do while I was at Kitt Peak was to create an image using this camera to show off how big the field of view was. And so I got this idea of using the moon as a comparison. So one night I went up to the telescope and took a picture of the moon and then waited a few days for the moon to move out of the way and then took a picture of the same location in the sky. And then using Photoshop, just sandwiched these two images together. And so this is actually the first image I ever created using the Kitt Peak telescopes. And while I was also up there, I also took the time to make this image of the Rosette Nebula. And one of the things I like to point out is these two images are on the same scale. And so it's just a good point that many of the nebulae we see out in space are actually, from an angular size perspective, very big. We just simply can't see them because they are too faint. So I made these two images and they came out well. And so I started making more images for Kitt Peak and then our sister observatory down in the Southern Hemisphere, Cerro Tololo Inter-American Observatory in Chile. And then the Gemini telescopes, which were just starting operation around then too, also asked me if I'd be interested in making images for them. And so I learned an important lesson in life at that time, which is if you do something once, it's a favor. If you do it twice, it's your job. And so I started making images for these observatories back in the late 90s. And then after that, I went to the Very Large Array Telescope in New Mexico, and then eventually ended up here in Alaska. But even though I'm now at the University of Alaska, I've continued over these years on just sort of a, just more kind of, I wouldn't call it a hobby necessarily, but I've continued to work with these different observatories in making images. So, a question that people often ask is why do we make images? What do the professional observatories do? Well, there's basically 3 reasons we do. And the first, and perhaps most obvious, is to visualize scientific results. If we're doing a press release, we want to have a visual with it so that people can see what it is we're talking about. And another reason we do is often to demonstrate new technologies. And finally, we also just like to make color composite images to share views of the universe. And so Here are some recent examples of work that we've done. So just this last week, we did a press release from the newly christened Noir Lab, which combines Kit Peak, CTIO, and Gemini, and will include LSST once it's operational. And so this was a press release we did to announce the DESI data sets. The data sets for the DESI survey would be available. And so we made color composite images from the data to show the quality and the depth of this data. We also, this is an image we released in the last few months. It was intended side-by-side images to show a ridge in, I believe this is M8, or it might be M17, I can't remember, where we were showing off the multi-conjugate adaptive optics system on the Gemini South telescope. So the point of these two images is to show how the adaptive optics improved the sharpness of the images. And then finally, we have a very small fraction of time that is made available to us on the telescopes, just simply for the purpose of having fun and making pretty pictures to share with the public. And so one of the really cool things about my job is that I get to use really big telescopes like 4-meter and 8-meter class telescopes to make color images, but I usually get a very small fraction of time. I only get a couple hours on each telescope each year. And so we choose what targets we'd like to do, but we also get some archival data and we'll make color images that way. So one of the things that a big difference I'd say between the professional observatories and amateur image making is that the images we make for the professional observatories represent the observatory. People often think that the color images that we release are the actual science. And so if you've ever watched any science movies, you'll see like the image appear on the screen and the scientist looks at it and says, oh, there it is. And that's the discovery. And so one thing I'll say is that very little of the data that is collected with our telescopes actually is used to make images. We do things like spectroscopy and photometry and polarimetry and measurements like that to do the science that we do. And it's only in a handful of cases to where we actually make an image from them. And those images represent not only the observatory, but the science and the scientists at the observatory and those who use them. So one of the things that we're very careful about is how we make our images and how they're represented. And so as a result, we tend to be, I'd say, behind the curve as far as the sort of the image processing techniques that we use, because we want it to be very simple and very clean and representing the accuracy and quality of the data as best as we can. And so this is one of my favorite Calvin and Hobbes cartoons. And one of the things I love about this was actually, he made this even before Photoshop existed. And so Bill Waterston had an eye to the future as to what, the kind of world we live in now where photographs can be modified and manipulated into any way possible. And so that's a real concern that we have is that we want people to know that the images that we make are real and accurate representations of the things that we see in space. So when I share our astronomical images, I often get questions like this. I say 9 times out of 10, the first question I get has to do with the veracity of the images. So people ask, is this what it really looks like? Are the colors real? Or my favorite is, if I were standing right next to this, is this what I would see? And so I don't know what it really means to stand right next to a galaxy, but you all get the idea. And so the idea here is that people want to know if the objects they're seeing are real. And in particular, they want to know if this is what they would see if they were closer. And of course, telescopes do much more than just simply magnify an object. They also amplify faint objects so they're bright enough for us to see. And they show us kinds of light that our eyes can't see. And so one of the challenges is that telescopes give us literally superhuman vision. They allow us to see things that our eyes cannot. And so the challenge in making these images is to faithfully translate what the telescope can see into something your eyes can see. And so the example I like to use is this. So this is a picture of the Horsehead Nebula as seen with the Mosaic camera on the Kit Peak 0.9 meter telescope. And so let's imagine you were to get in a spaceship and you were to fly out to the Horsehead Nebula. And then as you got out there, you would look through a portal in the side to see what you'd see. So if you, as you looked out the window of the side of your spacecraft, this is what you would actually see. And the reason that is because the surface brightness of an object actually doesn't depend on how close you are to it. And surface brightness is the ratio of how much light you get from an object to how big it appears. And so as you get closer to the object, you're getting more light from it, but that light is spread out over a larger area as the object gets bigger and bigger. And so one of the things, you can actually play this game at home. Walk towards a wall, and as you get closer to the wall, you'll notice that the wall gets bigger, but it doesn't actually get brighter. And so what this means is that if you can't see it with your eyes from here on Earth, you still won't be able to see it as you get closer. And so this picture right here is an accurate representation of what your eyes would see. And I think we can all agree this isn't very interesting at all. And so that's why we use telescopes. We use telescopes to show us things better or differently than what our eyes can see. So when people ask, is this what it really looks like? The answer is pretty much always no. There are some exceptions if you're talking about objects in the solar system that are lit by the sun and color calibrated. So a lot of the pictures that come from NASA, from Mars and places like that, they are color calibrated, or many of them are color calibrated to show what you would actually see. But the rest of the astronomical images we see, the answer is basically no. And part of it is surface brightness, as I talked about, but there's other factors as well. Our eyes are really bad at seeing color in faint light. We are really bad at seeing red light, which is why we put all the little red lights up around our observatory. And there's all these kinds of light our eyes can't see. So we can't see infrared light or X-rays or radio waves or things like that, but we can build telescopes that can. So a good question to ask is, if we make an image that uses X-rays, and people ask, is that what it really looks like? Well, unless you have X-ray vision, no, it's not what you're going to see. So when we make our color images, we can follow the same process that our eyes use, which is what's called the tricolor method. And that is, you mimic the way the eye produces color, and you can take images through basically red, green, and blue filters, and then you can combine them together to produce a color composite image that is often called a natural or a real color image. And I don't like using the term real color because it implies everything else is not real, but natural color is a term that we often use. But the thing is that we have a lot of filters that don't match up to the S, M, and L cones inside our eyes. And so we have filters for ultraviolet and infrared and things like that. And we also use narrowband filters, which I know, of course, are very popular in amateur astronomy as well. Kit Peak has like over 100 different filters available for the telescopes there. And so it gives us this power and latitude to create images in ways that are very different than what our eyes would actually see. And so one of the techniques that we started doing back in the 90s after Photoshop was capable of doing it was to create color composite images using more than the traditional red, green, and blue filters. So the picture on the right here shows an image of NGC 6822 as seen through 8 filters. And by combining, I think we used 6 broadband and 2 narrowband filters, we were able to bring out a lot more richness and detail in the galaxy. And so basically the method is straightforward. We take images through each filter and then assign a color to each filter. And what we usually use is what's called chromatic ordering, which is that we make the shortest wavelength light, the bluest or most violet color, and then the longest wavelength red, and everything is in order in between. And so you can see here that a galaxy, of course, looks very different through different filters. This is M33 through a blue filter. This is through an H alpha filter. And then we assign colors to them. And then for each filter, we assign a unique color. And in this case, we used, I think, 6 filters. And then the ultimate, once we combine them all together, the final image we get here looks like this. And so if we zoom in, by using more filters, we can get, we can see the nebulosity really well, and we can see the colors in the stars really nicely. Now, we use the same technique when we look at kinds of light that aren't visible light. So this is an example of a 4-color image produced entirely using infrared light. And so in that case, we use the same chromatic ordering method, which is we put the shortest wavelength is the bluest color, and then the longest wavelength will be red. And so we have red, green, cyan, and then blue. In this case, we use 4 filters. And then here is the final color composite image. So this image that you're seeing is made entirely with infrared light. So this is showing something in a way that your eyes would never see, but we are using color in the same way, that we're making the longest wavelength the reddest and the shortest wavelength the bluest. So one of the big questions we've had over the years is, if we have all these different filters and we can see things using all these different kinds of light, well, how can we make images, and what things are okay to do and what things are not okay to do? So after I left Kitt Peak, when I was at the Very Large Array, people challenged me. Well, how can you make a radio how we want to make images in the way that we considered to be faithful to what it is we're showing? And so we put a lot of thought into it, and then later realized that artists had already figured this all out. And so artists call this something called visual grammar. And visual grammar is basically the way our eyes interpret an image. So I'm going to give you a little bit of a challenge here. This image that you're seeing, in the chat window, I'd like for you to type in the answer to what you think is the answer to this question. So the question is, which half of this image is closer to the observer, the top half or the bottom half? So go ahead and type your answer into the chat window. Again, the question is, which half is closer, the top or the bottom? Okay, so I see a bunch of bottoms popping up. Okay, so that was the easy question. Now here's the hard question. How do you know that? You can go ahead and type your answer into the chat if you think you know. Okay, so I hear depth cues, further images are foggy, experience, which is very important, clarity, yes, familiarity with Earth context. So things like that. Trees in the bottom half are larger than trees in the top half. That's also part of it too. Yeah, so those are all good answers. So one of the things that's important to keep in mind is that whenever you look at something, a whole lot of things are going on in your brain. And in particular, your brain is trying to create a 3-dimensional model of what it is that you're seeing. And of course, this turns out to be really important in our day-to-day lives as we walk around and try not to trip over our cats and things like that. So our brains are constantly doing that. And even though this image on your screen is flat, we still can infer the depth, and there's several visual cues that we can use. One that was mentioned is that the trees in the foreground look bigger than the trees in the background. So that's a visual effect that if you see objects that have the same shape but are of different sizes, our brains will naturally interpret those objects as being intrinsically the same size, but the smaller ones are further away. Now, another really important visual cue here is the color. And so the top half of the image, you'll notice, is bluer than the bottom half, and that's because of the Earth's atmosphere. So as we look at the hills off in the distance, we're looking through more air mass, which means more scattered blue light, and that makes the distance look bluer. And this turns out to be a very powerful tool for our brains to figure out the distance to something. So our brains naturally interpret bluer colors, which artists call cool colors, as being further away than redder and yellow colors, which artists call warm colors. So cool colors are seen, our brains interpret as further away than warm colors. So one of the interesting stories of the Apollo missions is that the astronauts had a heck of a time actually walking around on the moon, because since there's no atmosphere, they lacked this visual cue. And so you can see one of the Apollo landers here, and you'll notice this part of the moon that's in the background. And if you look at it, you can actually convince your brain that it's either a small hill that's just right behind the lander, or it's a big mountain off in the distance. And so many of the astronauts were challenged because they lacked this atmospheric visual clue to help them gauge distances to things. And I think it was Apollo 14 with Alan Shepard, where they famously got lost on the moon. They weren't really lost, but they kept thinking they were very close to a crater, and it turns out the crater was a lot further away. So this is an example of a visual cue that our brains use. And so this is something that we can actually use as something to give images depth. And so one of my favorite Hubble images is this portion of the Lagoon Nebula. And this image right here has all sorts of visual cues in it that help our brains interpret the dimensionality of it. And one of the parts there is the color. And so the bluer areas in this nebula, our brains naturally interpret as being further away or in the background to the other part. And so people often ask, well, can Hubble see three-dimensionally? And the answer is no, it does not have stereoscopic vision. But the way the images are used in color composite images by Hubble and other observatories can give that feeling of depth and dimension. And so one of the really cool things is that objects like this, our brains really understand how to interpret it. And so it looks very real to us. It looks like a real place that you could possibly be. Whoops. So for comparison, here is a side-by-side images of the Keyhole Nebula from the Hubble Space Telescope. The one on the left, of course, is in color, and the one on the right is black and white. And if you look at the one on the right, it'll seem our brains have a harder time interpreting it. Without the color visual cues, it just feels flat, it feels more abstract, and it's really hard to understand what's going on. Whereas the color image on the left feels much more dynamic and alive. So as amazing as the Hubble Space Telescope has been as far as creating these razor sharp color images of the universe, I think in many ways, what its biggest contribution has been is pioneering use of color. And so people like Zsolt Levé and Lisa Furtari really developed a phenomenal ability to use color and composition and these other visual grammar tools to create images that we love so dearly. Now, there's other visual cues that we naturally rely upon. So for example, we naturally interpret red as being something that is warm, like a flame, and we interpret something blue as being cooler. Now, of course, when it comes to objects like stars, it's just the opposite. Blue stars are hotter than red stars, but in our normal daily experiences, people interpret red things as being hotter. And so a collaborator of mine, Kim Arkand at Chandra X-ray Observatory, has done studies to ask people which thing do they think is hotter, and that she'll show them red things versus blue things. And which thing they think is hotter depends on how much the science or astronomy they know. And so when we create color images, we keep these visual grammar tools in mind. But one thing I'll mention real quickly is I'm sure many of you enjoy, I love optical illusions. I love that sensation when your brain is being tricked into doing things. And all of these optical illusions are based on short-circuiting the wiring in our brains that are used to interpret depth and motion and things like that. And so this is a really cool one that was just posted on YouTube a few days ago on Veritasium. So if you want to go check that out, it's a fun example of an optical illusion. So what does this have to do with astronomy, and what does it have to do with the images we make? Well, when we make our color images, we are trying to tell a scientific story. We want people to be able to look at our images and naturally intuit the science of what's going on in the picture. So here's an example of where we used visual grammar to create a color composite image. So what you're seeing here is two pictures of the Triangulum Galaxy. The one on the left is one from Kitt Peak that uses only visual data. And the one on the right uses the Kitt Peak image, but we've added radio data from the Very Large Array Telescope. And in particular, we're adding what's called 21 centimeter radio data, which is a type of radio wave that's produced by cold hydrogen gas. And so we could have used any color we wanted for the radio waves, but what we ended up choosing was violet. And the reason why is because violet is a mix of red and blue. And we wanted that because when people look at the image, we wanted the cold hydrogen gas to blend visually with the red hydrogen gas in the H2 regions and the nebulae in here. We wanted people to naturally intuit that the cold gas is connected to the warm gas, and in fact, they're the same thing. And by using violet for the VLA data, it conveyed, since it has blue in it, it conveyed that it is colder. And so our hope is, and we've probably overthought this, but our hope is that looking at this image, people will be able to naturally intuit that the purple areas in this image are connected to the red areas, but they are colder. And that's actually what is happening. What you're seeing here is a map of the hydrogen gas inside the Triangulum galaxy. And you can see where the gas is hot and where it is cold. So far I've been talking about how we use color astronomical images to tell the story of science, but sometimes it goes the other direction. Sometimes we actually get science out of the color composite images. And one of the things that's really been fun over the years is when making these color composite images is sometimes I'll see something in there that looks interesting or unusual, and I'll go check and see if anyone knows anything about it. So over the years, I've managed to discover supernova remnants and other things like that. But one of the things that I've actually started doing is using color composite images to search for Herbig-Haro outflows, HH outflows that are produced in star-forming regions. And so this is an example. This is a picture of the Iris Nebula. And when I made this picture, I included hydrogen alpha just for the fun of it. And after I made the image, I noticed that I could see quite a few HH outflows, Herbig-Haro outflows inside the nebulosity. And one of the things that I think is really interesting here is because these nebulae are so interpretable by our eyes, our brains are actually able to interpret what's going on here pretty well. And so we can actually naturally intuit that we're seeing heavily obscured outflows that are embedded inside this nebula, not only because of their faintness, but because of what the nebulosity is doing around it. So this is an interesting example of actually using our naturally built hardware inside our brains to help us interpret three-dimensionally what's going on inside this nebula. And so when we look at the same nebula, just in hydrogen alpha, we can see these outflows a little bit better. But in this image, without the color cues, it's much harder to actually tell what is happening in there. And then when we look at it in the infrared with the Spitzer Space Telescope, we can see the embedded group of young stellar objects, the YSOs, that are actually powering these outflows. And we can see that there's at least 2 outflows that are being created by this embedded group of stars. And so this is an interesting example of how the color images actually enable the science. So one of the projects that I've been working on in recent years is using color composite imaging techniques to search for star formation in complex nebulosity. And so this is a picture of myself at Cerro Tololo Observatory in Chile. And using the 4-meter telescope, which is the silver dome on the left, we've been using a camera called the Dark Energy Camera, or DECam. And so here's a picture taken not by me, but someone else using the 4-meter telescope with DECam on it. And so here is a picture of DECam. It's this giant black thing at the machinery at the focal plane, the prime focus plane of the telescope. And one of the interesting things is that old telescopes like the 4-meter telescopes on CTIO and Kitt Peak turn out to be really good for these kinds of machinery because these telescopes are really big and massive and can carry heavy things. The newer telescopes like Gemini are much lighter and aren't designed to hold heavy instruments. And so this camera can be put up in the prime focus cage of the telescope. Here's a picture of the focal plane array. The DECam is currently the largest digital camera being used in astronomy. It consists of 62 2K by 4K chips, giving it 520 megapixels for a single image. And so this right here shows the orientation of the chips. Each of the rectangular bricks is a 2K by 4K science chip. And then you'll notice on the top and bottom in the corners, there are smaller chips that are used for guiding the camera. And one of the things that I think is kind of interesting and a little bit embarrassing for me to admit is just how insanely easy it is to use this camera. You don't have to focus it. You don't have to set up guiding. It handles everything by itself. You just simply write a script telling it where you want to point, how long of exposure, and it does it all. So observing with this camera is actually incredibly boring from the perspective of you mostly just sit there and watch it do its thing. Now, for comparison, this is just to give you a sense of scale. The field of view is 3 square degrees. And so here is the chip array with the moon superimposed on it. So you can see how large a field of view that we have. Now, even though we have a very large field of view, we have the pixel scale is 0.26 arcseconds per pixel. So we're getting sub-arcsecond sampling, even though we have this giant field of view. So my collaborators and I are using this camera to do surveys of molecular clouds in the southern sky, looking for evidence for star formation. So just to wrap up, I'll just say, if you're interested in seeing some of the images that I've helped to make over the year, most of the images I've made have been using NSF facilities from Kitt Peak, Sartololo, and Gemini, and we've accumulated all those images on the new Noir Lab image gallery. And unfortunately, I don't have my own personal gallery where I keep all the images I've made. I've made images using other telescopes, but by and large, most of the images that I've made can be found here. So if you just Google Noir Lab, which is the new name for our combined observatory, you'll be able to find that. And I'll also just shamelessly throw in a plug for a book that I wrote a few years ago that's called Coloring the Universe. And this book basically gives a behind-the-scenes view of many of the topics that I've talked about, basically how professional astronomers use telescopes and how we use a lot of the things that I talked about today in creating the color images, some of the color images I've shown you today. Okay, well, thank you very much. I'm going to stop screen sharing, and I'm more than happy to answer any questions that people may have. So Tom, if you want to handle the questions, I don't really know.
Okay.
So I guess I can start the QA.
Thank you, Travis.
Sure.
So Alex, let's see, you have a question. You can ask it in person if you'd like, if you want to unmute yourself. Okay. Oh, there he goes. Go ahead, Alex.
Are we okay? Can you guys hear me?
Yes.
Yes, we can hear you fine.
Okay, perfect. You answered the question a little bit there, right at the tail end, actually. I do some astrophotography myself and use, like, unfortunately PhD2 and, a lot of other, like, commercially available software. But right at the end of your presentation, you had mentioned about the camera kind of does all the work for you and guiding and capturing the image. So my question was in regard to, what kind of software do you use to be able to capture those and then guide such massive instruments and get such really cool high resolution photos?
So for the data acquisition, the actual operation of the telescope, the software is largely unique to each telescope. Each telescope has its own particular quirks as far as how it operates, and so the software is unique to it. All of the FITS files, all of the data are written out as FITS files. In the cases of images like with this camera where we have mosaics, where we have gaps between the chips, if we do a dithering pattern to fill in the gaps, then we'll process the data. Historically, to process the data, we've used a program called IRAF, which I think is best described as user hostile. It's not an easy program to use, and it's largely being supplanted now by Python-based software. And more, the data processing is become automated. And so when I use Decam, after we do the observations, in the next week or two, the data will be processed at the Noir Lab computing facilities, and then they'll become available in the data archive for me to download. And then at that point, I have just a giant, a series of FITS files to use. And the next step is then to use a program called FITS Liberator, where we convert the FITS files into 16-bit grayscale TIFF images. And then we load those TIFF images into Photoshop to do the color compositing and also to remove cosmetic effects and things like that. So those are basically the 3 steps in the process.
Okay, thank you. Let's see, Tom Curry has a question. His mic isn't connected, but why is green not a very common color?
In the astronomical images we see, or just in general?
I think he means in general.
So we don't see green stars because if a star is producing mostly green light, it's also producing a lot of the other colors as well. And so they all add up to produce white. And so when we see colors of stars, they're very patriotic. We basically have red, white, and blue stars out in space. I'll mention that in our astronomical images, we tend to steer clear of green and yellow. And the reason why is these are both very powerful colors that tend to overwhelm the rest of the image. And so if you look at astronomical images in general, you'll notice that they tend not to have a lot of those colors, in part because of the way nature works, but also because they are so powerful, because our eyes are very sensitive to green and yellow, and so they tend to overpower the composition of the image.
Okay, thank you. And let's see, we'll get Stephanie.
I've opened the Q&A window, so here, if you like, I can just go ahead and read them. I found where that is.
Okay, Stephanie, you can ask your question, or you can have a follow-up. Okay, yeah, go ahead. She says, go ahead.
Okay, so the question is, what would you like to see more amateur images of? Well, so I'll just say this. So first off, every day I'm blown away by the quality of amateur astronomical images coming out there. And I'll say for years, I've been a huge fan of Tom Polakis' work. And so you guys are knocking it out of the park. I'll admit the number of times I've polar aligned a telescope, I count with one hand, and each time I did a really, really terrible job of it. So the thing that I would say that amateurs are really, really good at right now is detecting faint extended structure. So whether it be faint extended structure in diffuse galaxies or nebulae. And the reason why that is because you guys have lots of time. I may have access to 4-meter and 8-meter telescopes, but I only get to use them for a couple hours a year. Whereas you guys, you may have smaller apertures, but I've seen images that are using, many months worth of data. And when it comes to faint extended structure, what matters most is actually the F ratio of the telescope and camera system. So on like the telescopes that I use, our F ratios are around F2, F3, which is very fast. But you guys, if you're around F6, F8, that's actually not that big a difference as compared to the just sheer aperture of the telescope. So if you compare 2 images of an astronomical object, one taken by a professional observatory and one taken by an amateur observatory, the big difference you tend to see is the professional observatory tends to be better at seeing compact sources like stars and unresolved galaxies, because we do really well at seeing faint compact things, because that depends primarily on how much light you collect, and that depends on aperture. And we've got you beat on the aperture. But you guys beat us on the amount of time that you have, and so you don't have the F ratio we have, but you can more than compensate with time. So the astronomical images that really blow my mind, the amateur ones, are the ones with just these beautiful nebulous scapes where you can see all this faint structure that we often miss in our images.
Okay, great, thanks. And that was from Stephen, not Stephanie. Sorry, Stephen. And Kevin has a question. Do you want to ask it, Kevin?
Sure. Can you hear me?
Mm-hmm. Can hear you.
Yeah. So my question is, when I image something, I'm always trying to figure out what is the correct color. So, because I'll see, very purple-looking versions of Orion's Nebula or very pink ones. is there a resource you use that you think is, the gold standard for what these things should look like when they're complete?
Yeah, that's a really good question. So we don't have, we have rules and guidelines, but we don't have like a set color scheme that we use every time. And the reason why that is because almost every time we're using different filters. Or from different telescopes, or maybe looking at different objects. So when we use broadband filters, we always use what's called chromatic ordering, which, as I described earlier, we make the longest wavelength filter correspond to the reddest light and the shortest wavelength to the bluest, and everything is in order in between. When it comes to using narrowband filters, basically there are no rules at all. And so it is subjective to a certain degree, and you will definitely notice particular styles amongst different astrophotographers is what they use. I can look at an image and tell right away that Zolt Levé was involved in making it. So different people have different styles. I have my own style, I think. And so it does get to the question of, what is the right one? And there isn't a right one, but at the same time, that doesn't mean you can just do whatever you want. And so again, we use the rules of visual grammar to try to most accurately represent the way people see things in a way that will be most intuitive to them. So that's a long way of saying I can't help you.
Thank you.
Okay, Bill Peters, go ahead and ask your question.
Yeah, how do you eliminate satellites, airplanes, and stray light in your pictures?
Well, our adaptive optics system uses lasers, and so we can blast the airplanes out of the sky with that. The satellites are harder to hit because they're further away. Well, in all seriousness, we can't do that. In fact, we once got in trouble because we had our adaptive optics system going on while a plane was nearby. The answer is pretty much the same way everyone else does, which is just take multiple images, and then as we stack them, use rejection algorithms that will reject pixels that are saturated by star trails. But as many of you are probably aware, these satellite constellations that are being launched, like Starlink, are going to be a huge problem for us, and especially for these wide field imaging cameras like Decam that I'm using now, and the camera that will be on the LSST telescope, which can see a very large field of view. And so one of the major concerns we have in astronomy right now is that as more and more satellites are put up into space, and we get these constellations of thousands of satellites, they will have major impacts on the astronomy that we do.
All right, thank you. I think that wraps it up for the Q&A. Last call for Q&A. Thank you, Travis.
Can I ask a quick
go ahead,
question?
Tom. Go ahead.
Travis, this is kind of a pre-COVID question, but do you still travel to observatories, or is that all done remotely and with telescope operators at the sites? Like, you still go to Chile or to Arizona to observatories?
It depends on the telescope. So the CTIO 4-meter telescope is now we can operate it remotely. So I will be logged in from my computer. And so just actually this last October, I was doing that. And while I miss being at the observatory, it sure is a heck of a lot easier than trying to get from Alaska down to Chile. For other telescopes, I still need to travel to them. And so all of the telescopes on Kitt Peak, you do still need to actually travel there. So the good news is I still get to come to the telescopes and mountaintops. The bad news is I still have to travel the telescopes and mountaintops. But we are seeing in astronomy that it is becoming more and more automated. And so, like a LSST, the data acquisition and processing will be 100% automated. And so we are seeing a change in how our profession is being done. It used to be that to be a good astronomer, you had to be a master at machinery and photographic techniques and fixing things on the fly as they break. And now it's turning more and more into you need to be really good at being at coding and analyzing big data, using machine learning and techniques like that. So it's interesting to see how the profession has evolved over the time I've been in it.
Thanks.
And one more question popped up about the Starlink arrays. Have you had trouble with those yet?
I personally have not, but our observatories have. And I'll just relay the story that the last time I was observing in Chile in 2019, it was near, the sun, it was morning twilight. I had closed the telescope up and I was, just going outside to just enjoy the majesty of the sky before heading off to bed. And then I looked over and I just saw this massive sweep of satellites. And if I hadn't known what it was, I think I would have peed myself, because it was just unlike anything I'd ever seen before. It is worth mentioning that these constellations are most visible near sunrise and sunset. Once you get later in the night, the satellites will be in the shadow of the Earth, and so will be reflecting less light. But it is a major concern, because that those times of night we are doing observations, especially of solar system objects that are maybe close to the sun, and so we can't see them around midnight. And so we are definitely concerned about the impact it'll have on our science.
Okay, let's see. I think you're happy with the answer, right, Kevin?
Yes.
Okay, any more? Going once, going twice? All right, gone. Thank you very much once more, and I'll turn the meeting back over to Gordon.
Okay, well, thank you very much for having me tonight. It was a pleasure talking with you all.
Thank you.
Oh, yeah, Travis, thank you. Thank you very much. That was very interesting and close to a lot of us also who are out there playing around with our cameras and working to get better and better every night and understanding our equipment. So thanks a lot. This came down to our level, I should say.
Well, thank you very much.
Very much of us.
Well, I'd like to thank both the Toms for inviting me. It's been a lot of fun.
Okay, good. I think that will do it. Remember, 19th of February is our next meeting. Will be about what's going on at Lowell Observatory. So we'll all want to know that when things start opening back up. And remember again, dues are due. And please help the club out by updating your dues. Help the club to open back up this year by renewing your membership and getting more people to come on in. So that's all I have. Again, fantastic meeting again. Thanks, Tom Mosden, for putting this on. Tom Polakis, again, thanks for your presentation. And remember, guys, anyone that has a subject that they want to give a quick 10-minute presentation on, member presentation, let me know. I will give a countdown as usual, and that will close this month's meeting. I will see you again on the 19th of February. 3, 2, 1. Bye, y'all.